All right, so now let's talk in a little bit more detail about some of the things we've learned concerning neurons and synapses and neurophysiology and things like that. And so I want to just give you some examples of different neurotransmitters and then use those to sort of explain some phenomena you might be familiar with. And so I'm going to talk about common neurotransmitters in this lecture, and then in a future lecture we're going to talk in some detail about sensory organs. So let's go back to our figure which shows the anatomy of a synapse. And you remember that a signal comes in from the presynaptic neuron, and that causes vesicles to be released that contain these neurotransmitters. And the neurotransmitter is a chemical that drifts across that synaptic cleft and binds to a receptor on the postsynaptic neuron. And when it binds, it changes shape, and that does things like that opens up ion channels. And so it might open up channels that let sodium comes in, which is going to excite that neuron and make it more likely to fire. Or it can open up channels to let things like chloride or something else in, which is going to hyperpolarize that postsynaptic neuron and make it less likely to fire. And then once the neurotransmitter carries its signal to the postsynaptic neuron, then it can be released and go back to the presynaptic neuron, get packaged up, and then get used again the next time a signal comes down. And so we talked about one example. I think we talked about acetylcholine in our first example. That's a very common neurotransmitter, but there's lots of other ones, and you've probably heard of some of these. You might be familiar with some of them, but we can talk in a little bit of detail now about exactly what these neurotransmitters do. And so big picture stuff, sometimes your body doesn't naturally produce enough of these, and so your doctor might prescribe them. And so sometimes if you don't feel good, or if you have something going on in your head, one of the reasons might be you're not producing enough of a neurotransmitter, and so just by taking some of that neurotransmitter you can alleviate those symptoms. Some drugs work by mimicking neurotransmitters, and so these are chemicals that are very similar in shape to a neurotransmitter, and so when you take those drugs, that stimulates neurons that are stimulated by these other neurotransmitters, and that has an effect. Some molecules inhibit the binding of neurotransmitters, and so maybe you produce enough of the neurotransmitter, but it can't bind, and since it can't bind, it can't transfer the signal to other neurons. And so if you have a substance that interferes with the binding of a neurotransmitter, that can have consequences. So just broad examples here. Let's just talk about some of those. So you're probably familiar with endorphins. You hear about endorphins all the time. In general, and again, we're taking the 10,000 foot view here. In general, endorphins are a type of neurotransmitter that makes you feel good, right? Or makes you feel better. Like if you have endorphins, they're carrying signals, and those signals in general make you feel better, for lack of a better word. And so that might mean you might have less pain, or you might have a euphoric feeling or something like that, right? And so what do these endorphins do specifically to cause you to feel better? Well, there's lots of ways. Again, we're taking the 10,000 foot view, but one method involves presynaptic binding. So break that down. Presynaptic, before the synapse. So these endorphins might affect things before the synapse. So, for example, pretend you're running and you pull a muscle, right? What does that mean to pull a muscle? You remember what the physiology of a muscle? You stretch that muscle so much that you actually rip fibers apart, all right? And you break open those cells. Your body needs to tell you this happened, right? You need pain receptors that lets you know when you've damaged tissue. Otherwise, you'll just keep damaging it more. That's kind of why you have pain, right? And so when that muscle gets ripped open, those pain receptors start firing and sending a signal to your brain, hey, you know, you've hurt yourself in this area. You get a sensation of pain in that area. This would be part of the peripheral nervous system, right? It's taking a signal and carrying it to the central nervous system so the central nervous system can figure out what to do with it. But endorphins inhibit the release of neurotransmitters for those pain neurons. So for that pain neuron to send a signal to your brain, it has to send it up one nerve and pass the signal to another nerve and pass the signal to another nerve, right? Part of the peripheral nervous system. Pass the signal to the central nervous system. But the endorphins, but let me back up here. You know, for that first pain neuron to pass its signal to the next pain neuron to pass its signal to the next pain neuron, you have to have synapses, right? You have to have places where the first neuron releases neurotransmitters to cause the second pain neuron to fire, and it has to release neurotransmitters, and so on. Your endorphins can block the release of those neurotransmitters. So although that first pain neuron is firing because the muscle got pulled, the endorphin blocks the release of neurotransmitters before the synapse. And so now that first pain neuron doesn't release neurotransmitters, so the second neuron doesn't fire and the third neuron doesn't fire, so no signal makes it to the central nervous system, and so you don't have as great a pain as you normally would. That's just a rough example of how endorphins might, you know, make you feel. So how does it make you feel better? You have less pain. Those pain neurons want to fire, but the endorphins are blocking it. And so that's kind of what we're showing you here, right? For the pain neuron to pass its signal, it must release some kind of neurotransmitter to cause the next nerve to fire. But if the endorphins block the release of that neurotransmitter, pain neuron not firing, you don't hurt as badly as you would. Okay, so that's one rough example of how endorphins can make you feel better. Here's another. So in the brain, you know, so now we're in the central nervous system, not the peripheral nervous system. You have neurons that make you feel good, or the opposite of pain. So again, you know, I'm no neurologist, and you know, I don't have any technical terms to use here, but in general, you understand this, right? Your brain processes signals, and if certain nerves fire, that makes you feel better. It's the opposite of pain. These neurons often use a neurotransmitter called dopamine. So you've probably heard of dopamine before. And so dopamine carries signals among these neurons that make you feel good. And so consequently, if you have more dopamine in your brain, more of these euphoric neurons are going to fire, and you're going to, in general, feel better, right? Now recall that most neurons have excitatory and inhibitory synapses, right? And so every neuron's got other neurons coming into it, and that's what your brain is. Your brain is billions of these neurons, and they're all connected to each other in all these complicated ways, and they all come together to produce consciousness and do all the amazing things your brain can do. But at the center of it, you've just got all these synapses connecting one neuron to another, and sometimes they inhibit this neuron, and some of these will excite that neuron, and they're all fighting it out to determine which neurons fire and which ones don't fire. Well, if the excitatory neurons win, then dopamine is released, which causes other, neurons that are part of your pleasure centers to fire, and you feel good. If the inhibitory ones win, then you don't release as much dopamine. And so those euphoric neurons don't fire as much, and so you feel bad, you feel less good. Well, endorphins make you feel better by inhibiting the inhibitory synapses, right? So we're going down a rabbit hole here, but think about it. You've got inhibitory synapses that cause your pleasure centers to not release dopamine. And so if those synapses win, you don't release dopamine and you don't feel good. Endorphins inhibit those inhibitory synapses, so they don't win as much. They don't shut the neurons down like they normally would, so the pleasure centers fire more often and you feel better. And so endorphin, again, it's the same as we talked about before with the pain neurons. It's inhibiting the release of a neurotransmitter. So, is endorphin a neurotransmitter itself? I don't know. This is neurophysiology, and there are people who know a lot more about this that you should ask. So I don't know if it's considered a neurotransmitter, but it does act by inhibiting the release of other neurotransmitters. And whereas before it was inhibiting those neurotransmitters in pain neurons in the peripheral nervous system, in this example, it's inhibiting neurons that are in the central nervous system, but it's inhibiting those neurons that inhibit other neurons. So it's sort of like, the enemy of my enemy is my friend, or something like that. By inhibiting an inhibitor, you are promoting the firing of these neurons. They are your pleasure centers in your brain. So that's pretty cool. But again, it just goes to show you how ultimately it's just chemical reactions, and which chemical reactions are more common when and cause certain neurons to fire, and that's what makes you you. So if the endorphins inhibit the inhibitors, that means the excitatory neurons win more often, so more dopamine is released, the neurons in your pleasure centers fire more, so you feel better. So that's what endorphins do for you. That's how they work at the molecular level, by inhibiting certain neurotransmitters. This is something sometimes what you call a runner's high, so you're running and you're kind of stretching muscles and you're releasing endorphins, and when your body releases endorphins, so you don't get overwhelmed by the pain, those endorphins can affect lots of neurons in your body, and those endorphins inhibit these inhibitory neurons, so your pleasure centers can fire more, so you just feel happier, you just feel better. Okay, so this is getting a little complicated, but the bottom line is you got many reactions all taking place simultaneously. And it's this complicated interaction of neurotransmitters from all these different inhibitory and excitatory neurons. They all sum together to create your current mental and physical state. And so I've said it before, I'll say it again. You are nothing more than a complicated set of coordinated chemical reactions. That's what you are. That's what's going on in your brain right now. Okay, let's use drugs as another example of how these neurotransmitters can work. So the endorphins, inhibit these inhibitors. They, in general, make you feel better. What if you ingested a chemical that mimicked an endorphin? Right? What if you had a chemical, a molecule, that had a very similar shape to an endorphin? Well, this molecule would bind to endorphin receptors, and it would have the same activity as endorphins. It would do the same thing. It would inhibit neurotransmitters, and it would cause certain nerves to not fire, the result being other nerves would fire and you'd feel better, right? Well, what if you had this synthetic molecule and you took it and it actually worked a little bit better than your natural endorphins? And so it binds to that endorphin receptor, but it binds more tightly and it doesn't let go. And so that endorphin-like activity would persist, right? The endorphin receptor is constantly stimulated. The end result, again, we're talking about your pleasure centers, so dopamine is constantly released. Well, that's what happens when you take things like morphine, right? Morphine sounds like endorphin because they are the same class of molecule. They're very similar shaped molecules. So things that we call drugs, drug starts to become a difficult word when you start to talk about brain chemistry in that, right? Because brain chemistry is just chemistry. Like you think of drug, oh, that's a chemical that we produce. But that's what you are, is you're just chemical reactions, right? So a drug might be something that you could say, well, it's synthetic, it's not naturally produced, and it's got a little bit different shape than the normal one. I don't want to get into those arguments because I don't know anything about those arguments, right? But you can see how something like, morphine can give you pleasure, and it can really, reduce pain because it mimics things that your body already has, and it just makes them more intense and work better. And so that's why what a lot of drugs, probably all drugs, do is that they take things that are already in your body and they kind of hijack them. And so morphine, heroin, opioids, that's why they work, is because they're shaped similar to endorphins, but they bind more tightly to those endorphin receptors. And they have a wider range of receptors that they bind to than regular old endorphin. And so that's why they have such an intense effect on your brain, is because they have just a little bit different shape that makes them work a little bit better. And so, like I said, lots of things that we call drugs, this is why they give you a feeling of euphoria, or this is why they have an effect on your body, because they have a similar shape to neurotransmitters, and they work at that neurotransmitter level, and so then they can stimulate, they can inhibit inhibitors, which actually stimulates other neurons that you have, and that makes you feel better. So, for example, marijuana has compounds that mimic other neurotransmitters. Nicotine mimics acetylcholine. And so a lot of these things that we take, why do we take them? Because they make us feel better. Well, what exactly is happening? They are mimicking neurotransmitters. They're binding to their receptors. They're causing these neurons to fire an abnormal amount. And so a little bit, makes you feel a little bit better, but of course you can see why it's easy to get hooked on this, right? And it can spiral out of control because these things are designed to make you feel better. Who doesn't want to feel better? But of course, it's difficult to sustain, and there's long-term effects to your body that are negative and outweigh the short-term benefits. Now, another example that works at this neurotransmitter level is cocaine, which again is just a recreational drug that people use. And it also works on, neurons that use dopamine, right? Remember, dopamine is a neurotransmitter that is used for nerves in your pleasure centers. So the neurotransmitters, like dopamine, bind to the postsynaptic membrane, then they're released and they go back to the presynaptic neuron, right? And dopamine is no different. And so dopamine is working in these nerves that are part of your pleasure center. And so, carry one pleasurable nerve to another pleasurable nerve, dopamine carries that signal. And it binds to the membrane of that postsynaptic neuron and opens channels and causes it to fire. And then the dopamine gets released and it goes back to the presynaptic neuron, and then it can cycle again, right? To get back to that presynaptic neuron, it needs a transporter. It needs a molecule to help carry it back to the original neuron. And so it's kind of this step here in this figure, in this process. If this were dopamine, dopamine would need a helper or a transporter to get it back to the original neuron. That's just how it functions. Now again, remember, dopamine is working, these neurons are neurons in your pleasure center. Well, how cocaine works is it binds to this helper protein. And so cocaine does not necessarily bind to anything on either nerve, but it binds to this helper and it ties up that helper. And so that helper cannot carry dopamine back to the original neuron because the helper is bound to cocaine. So the dopamine just sits there in that postsynaptic neuron. It stays, or actually it doesn't stay in that receptor, it stays in the synaptic cleft. So the dopamine has been released from the postsynaptic neuron, and it's in the cleft and it's ready to go back to the presynaptic, but it can't because it needs that helper. But that helper is tied up by cocaine. So the dopamine just sits there in that presynaptic cleft. Well, what's going to happen? If it's just sitting there in that cleft, eventually it's going to go right back and bind to its receptor again on the postsynaptic neuron. That's what dopamine does, right? And so it's going to cause that postsynaptic neuron to open up sodium channels, and it's going to cause that postsynaptic neuron to fire. All right? So instead, but it's causing that postsynaptic neuron to fire even though it didn't receive a signal from the presynaptic neuron. It's just going to sit there and it's going to keep stimulating that postsynaptic neuron, right? But remember, that postsynaptic neuron makes you feel good. And so you sniff a little cocaine, now you feel good, right? This is where you get that sense of euphoria. But of course, it doesn't last. There's a downside. The dopamine just keeps binding to its receptors, keeps stimulating that postsynaptic nerve, and you get excessive euphoria. And so again, you get this chemical reaction that's causing you excessive euphoria. Well, in the long run, what might happen here, right? That's in the short term. But what if your body was constantly stimulated by dopamine? You know, you've got that cocaine in your body, and that helper molecule is bound up, so the dopamine doesn't go back to where it started, and it keeps stimulating that neuron. One thing your body's going to do is down-regulate those receptors, right? Your body's making all these receptors, but it finds that it doesn't need all those receptors. You've got this dopamine that just stays there and keeps firing that neuron. You don't need as many receptors anymore. So you down-regulate the receptors, right? Why make more receptors when you're getting the same effect with fewer receptors? Why waste that energy? Okay, but then what happens if you remove the molecule that caused that excessive dopamine release? What happens if you stop taking the cocaine? Now the dopamine can cycle back to its original neuron. So the dopamine doesn't sit there and keep stimulating that postsynaptic neuron. And so remember, that postsynaptic neuron was in the pleasure center, so now it's not firing as much. And whenever you do try to fire that neuron, when the dopamine does go into that synaptic cleft, it has fewer places to bind to. And so you don't have enough dopamine to make that neuron fire. And so now you go from these feelings of excessive euphoria to you can't get that nerve to fire at all. And so you feel miserable. And so that's addiction. That's what happens, is the neurons in your brain change. And so then when you remove the drug or whatever you were hooked on, you have changed the physiology of your neurons. So they don't work like they normally did. And now you feel absolutely awful. And the only way to make yourself feel good is to go back to the drug. And that's addiction, right? And so that's why it takes work, and it's very hard to go cold turkey. That's why you need a program to try to reprogram and rebuild those neurotransmitter receptors and things. And so anyway, that's a very simplified example. It's a lot more complicated than that, but it's a basic level. You can understand this now. You can understand how what's going on in your brain is just molecules flying across these synaptic clefts. and breaking down and being reabsorbed, and other things that you take that affect that can have a big influence on whether or not your neurons fire, which is going to have a big influence on, your psychology and how you feel. Okay, let's talk about some other drugs that you're familiar with. Very briefly, let's talk about NSAIDs, non-steroidal anti-inflammatory drugs. Advil, Aleve, right, ibuprofen, common pain relievers. So how do these work? Well, this is a whole different mode of activity. But again, the idea is that by understanding the basic physiology of neurons, you can understand a lot of other things. These particular drugs block the COX-1 and COX-2 enzymes. Okay, what do those do? Those enzymes make other molecules called prostaglandins. Okay, what do those do? Prostaglandins are kind of like a hormone that enhances nerve firing. They're kind of like a neurotransmitter. Again, what exactly is a neurotransmitter versus a hormone? Some hormones act like neurotransmitters. I'm not qualified to give you specifics on that, but prostaglandins are like hormones that enhance nerve firing. So they are kind of like a neurotransmitter. Anyway, the COX-1 and COX-2 enzymes make these prostaglandins, and those things cause nerves to fire. But if you take ibuprofen that blocks those enzymes, then you don't make the prostaglandins, then the nerves don't fire, and you have less pain. So we're specifically talking about nerves that give you pain. So if you have a headache or if you have a sore muscle, those pain nerves are firing and you don't feel as good. You take these NSAIDs, you block the COX-1, COX-2 enzymes, you don't make the prostaglandins, so those pain nerves are less likely to fire, so you don't hurt as much. See? So again, changing your physical and mental state just by changing your body chemistry. You are just chemical reactions. But I am too, so. Okay, so again, just by having a basic understanding of neurons and how neurons work, you can understand other things like anesthesia, right? And so anesthesia is kind of an incredible thing, right? I can take a drug, I can inject something or whatever, and then I don't feel any pain. You can stick a knife in me and you can slice me open and I'm cool with it, right? And there's lots of different anesthesias and lots of different ways they work, but again, by understanding how nerves work, you can kind of get a picture of this. For example, local anesthetics. And so, they give you a local, they don't knock you out, but they're going to cut a wart off or do some, cut a mole out or something. They might, when they pull your wisdom teeth out, they inject a little local anesthesia. And so you're numbed. You don't feel any pain there, even though they're cutting you open. Well, there's lots of those, but some of those work by blocking sodium channels. Well, now this makes sense, right? The sodium channels open in the nerves, in the pain nerves. It allows sodium to rush in. That creates a signal. That signal gets passed and you feel pain. But if you put this molecule in that blocks that sodium channel, now sodium can't flow in, the pain nerve can't fire, and so you can damage the tissue, but you don't feel pain. See how that works? No influx of sodium, no action potential, no pain. So this is a very basic, again, there's lots of details here. I'm no expert on any of this, but by having a basic understanding of neurophysiology, you can start to understand how some of this stuff can work. Okay, so cool. That was just a little bit of detail about neurotransmitters. Again, the 10,000 foot view, but you can see how these different things can react with different molecules on your cells and can cause a nerve to fire or not fire. It's pretty cool. Okay, so that's all I have for this section, and I'll talk to you later. See ya.